Okay, so this is going to be our first lesson, and we're going to talk about the Fourier transform. Like I mentioned in the introduction video for this week, we're not going to talk about PDEs in this class until next week. Obviously, we're going to talk about PDEs, but we're going to talk about, this week, we're going to talk about Fourier transforms, which is a tool, among other things. We're going to use it as a tool to solve partial differential equations. So I'm just going to read this little blurb here. The Fourier transform and the related Fourier series, which we will cover later, is a tool that is ubiquitous in science, engineering, applied math, and math, like theoretical math. It gives a way to represent functions as a continuous sum, that is an integral, of complex exponential functions. It is related to the Laplace transform, which you probably remember from differential equations, though in practice the two tools are used in different scenarios. But still, like the basic outline of using the Fourier transform to solve PDEs will be very similar to the outline of using Laplace transforms to solve ordinary differential equations. Okay, so first I want to set up a few definitions. So you're gonna have to forgive me as I kind of navigate my new arrangement in here. This is the first time I think that I've taught an online class from this room, and I have furniture. Like there is a big chair right here that I'm bumping up against, so you might see that from time to time. So first, we're going to assume that our function f is absolutely integrable. I'm going to abbreviate that also because I'm bad at spelling. This is absolutely integrable, meaning if you look at its integral from minus infinity to positive infinity of the absolute value of f of x, this both exists and is less than infinity. So this is an improper integral. Okay, so we have to, if we were to look at this rigorously, you would do the limit of the upper limit goes to infinity, and the bottom limit there goes to minus infinity, something like that. But we want to make sure that this integral is finite. Okay, and again, if we want to kind of look at this rigorously, this is the limit, I'll say, as a, b. Both of these go to infinity, and it's going to be integral from minus a to b. So minus a is going to minus infinity, b is going to positive infinity of the absolute value of f of x dx. And this is a double limiting procedure, so the idea here is no matter how we take the limit b and a going to infinity, this has to exist. So in other words, it's not just going from minus a to a for like a symmetric limit or something like that, though since it's an absolute value, it doesn't matter. Sorry, this is just kind of another way to say this would be something like this, minus r to r, the absolute value of f of x dx. Now, ordinarily, these two limits might be equal to each other, or sorry, might not necessarily be equal to each other if we didn't have absolute values here. Since we have absolute values, they're equal to each other. And so what we only want to look at functions for which this equality is true here. That is, for which this integral converges. Okay, the definition of the Fourier transform, I will give it to you now. The definition is the following. The Fourier transform of the function f. Okay, what's going to happen is going to take a function f. F is a variable, f is a function of the variable x, and it's going to transform it to a function of the variable omega. And this is the definition. This is 1 over the square root of 2 pi, and it's going to be from x equals minus infinity to positive infinity, f of x e to the minus I omega x dx. Now when we do this integration, sorry, see that light's kind of maybe glaring here. This is e to the I omega x, and that just says dx there. I don't know if I can. I tried doing this with the lights off, and the lights off did not work. Sorry, I will feel like an idiot now. The lights off did not work well. Anyways, okay, so this is the definition. Once you do this integration, x is no longer a variable. Omega is the variable. We're not integrating out the omega variable. We're integrating out the x variable. And so this is going to give us a function of the variable omega. Another popular notation for this is f hat. So we're going to have f hat of omega. Now, there is a warning that I want to give here. I'm going to even write it on the board. Warning. Not all people define the Fourier transform this way. There are several different ways to define the Fourier transform. Some have it without that 1 over the square root of 2 pi. As we go on, we'll see why that's there. It looks kind of mysterious now. Some people have it without that and keep it like this. Some people define it with that, but put a 2 pi here. Some have a 2 pi here and without that there. I think in the official course textbook for this class, there's not a minus sign there. It does it with a positive sign, which for us is going to be like there's not a minus sign in the Fourier transform in the book. There's just like that without the minus sign. For us, that's going to be the inverse Fourier transform. So there's all of these different ways to define what the Fourier transform is. They all basically do the same thing. It's just a matter of like when we actually apply it to formulas, we have to know the specific one we're dealing with so that our formulas are correct. But as we will see, or not as we will see, as you can see, whether you solve a PDE using this definition or another definition, you're going to get the same solution. But I'm going to use this as the definition for the Fourier transform, and that's what I would want you to use like on your homework assignments and tests and that sort of thing, just so it's consistent in this class, that is. Okay, so again, what we're doing here is we're putting in a function of f and we're getting out a function of omega. Now, one way to think about this, if we think about, let me just read what I have here. If, for example, we think about the function f of x as being an audio signal, so here we would think about x as being a function of time, or sorry, we think about x as being time. F hat of omega is the amplitude of the portion of the signal at frequency omega. So if you have like an infinite number of instruments playing or something, and we have one instrument playing a note of omega, whatever note corresponds to a frequency of omega, the amplitude, like the loudness of that musician playing the note at frequency omega, is going to be the Fourier transform of that. Okay, so it's a way to break a function into its constituent pieces by their frequencies. Okay, and we're going to see how we can recover the function f from its Fourier transform. That'll be in a couple of videos from now. Okay, so one thing that we need to ask is this well defined? We have an integral here. We have an improper integral. Whenever we have an improper integral or any sort of like infinity thing going on, we have to make sure it converges, because if it doesn't converge, then it's not a well-defined thing. If this integral, like we have an infinite integral here, under the hood, it means there's something like a limit going on here. And if the limit doesn't converge, then this is meaningless. So we have to ensure, or I guess speak to what, does this make any sense? So in other words, I want to ask, excuse me, so in other words, I want to ask, does this integral converge? Is it absolutely convergent? Okay, and it is based on this assumption here. So if you look at something like 1 over the square root of 2 pi times the integral x equals minus infinity to positive infinity of the absolute value of f of x e to the minus I omega x dx, okay? So now it's important to realize here that f could be complex valued, and this exponential function is definitely complex valued. So these absolute values here, I will say absolute values, but it means the complex modulus. This is equal to 1 over the square root of 2 pi times the integral x equals minus infinity to positive infinity times the absolute value, or the modulus of f of x, and then times the absolute value, or the modulus of e to the minus I omega x dx, and I'll set out of the way so you can see what I just wrote. Okay, now e to the minus I omega x, this is a complex number that is on the unit circle. So its modulus is always going to be equal to 1. The modulus of this is always going to be equal to 1. And so what this is 1 over the square root of 2 pi times the integral x equals minus infinity to positive infinity times the absolute value of f of x dx. And we know by assumption that this integral converges. That's what it means for f to be absolutely integrable. And so that converges and is finite. So the function that we put in here is absolutely integrable, again, meaning this right here, the absolute value of f of x, that integral exists and is finite, okay? If f is absolutely integrable, then this definition of the Fourier transform is completely well defined, just kind of in terms of basic Riemann improper integrals. Now, we're actually going to see what happens, in limited cases, we're going to see what happens if the function that we put in there is not integrable, okay? Because we can actually extend this to a large class of functions. We can actually extend it to such a large class of functions that we're not just doing Fourier transforms of functions anymore, we're doing Fourier transforms of distributions. And you might remember one of the most famous distributions, really the basic one we're going to talk about, is a Dirac delta function. It's not really a function, it's called a distribution, but we'll get to that a little bit later. Okay, that's all that I want to talk about today, or not today, for this video. This is an introduction to the Fourier transform. This is the definition of a Fourier transform. I will give an example of computing the Fourier transform of an actual function in the next video.